So let's take a look at our first topic in general relativity. It's the gravitational redshift. I'm sure all of you are familiar with it from the discussions in the popular science literature. Just the statement that clocks near a massive star run slower than clocks far away. Clocks deep in a gravitational potential run relatively slowly. We want to see that this is a prediction from the equivalence principle, okay? And so it goes all the way back to the fundamentals. Okay, we'll want to see that, it applies to situations where we can approximate the gravitational field as uniform, and that what's important here is the change of the gravitational potential as a function of distance. So here, let's do it from two different perspectives. There are several others done in the textbook as well. Okay, so we'll start here with a situation of an emitter or an observer sitting on this planet, okay, and sending a light ray up to an observer at a higher height. Okay, so gravity is acting, acceleration of gravity is acting downward, and it's approximately uniform over this region. So the fellow on the surface of the planet, or at some fixed radius, perhaps above the planet, sends a light signal to another observer that has a fixed position above the planet. He sends a light ray there and tries to communicate with him with a particular frequency nu. Okay, well, this is the physical situation, but we know from the equivalence principle that we can relate it to a similar problem in an accelerating reference frame in an otherwise inertial frame where special relativity holds. So I consider the emitter at the base of a rocket ship that's accelerating upward with an acceleration of g. G matches the g in this problem. Okay, and it's sending a light ray from the base of the rocket ship to the tip of the rocket ship where there's an observer which absorbs it up there, and the height of the rocket ship is taken to be h. Now, this is a problem in which gravity is weak, and so I use basically Newtonian estimates on my times and distances, and I'll get results which are correct to first order in small corrections from the Minkowski metric. To do better, well, I'll have to just develop the formalism of general relativity, and we're not there yet. We'll be perfectly happy to get first order effects now. Of course, some first order effects can be written down as a differential equation, which can then be integrated, and we'll do that sort of thing in the textbook as well, and in the lecture series. I hope that you're following along in supplementary lecture number 11, because it follows the videos very, very closely and puts in all the details that I just mentioned as we go here. Okay, so let's take a look at the problem of redshift from the perspective of the rocket. Light leaves E at a time t equals 0 and arrives at O, travels a distance h, so it takes a time which is h divided by light's universal velocity c. Okay, and then O picks up the light ray. Okay, it's emitted at a certain frequency, okay, which I call nu sub e. Okay, the frequency that of the generator that the emitter has. Okay, now O, of course, he's receding at a velocity which is just the acceleration times the time. Okay, I say that the rocket took off at time t equals 0 when the light ray is being sent up the rocket. Okay, so the velocity of the rocket after a time t is acceleration times time. Okay, the time, that's the time for the light to go from the bottom to the top of the rocket is h over c, and so that's the velocity. Okay, well then the observer O sees the light ray coming in, and the light ray of course suffers from the Doppler shift. Okay, so the frequency that is emitted is related to the frequency that observed by the formula of the Doppler shift, the longitudinal Doppler shift that we derived in special relativity. Okay, in the lecture notes, it's discussed again, and also just look back at your special relativity notes to grab that formula. So here's the general formula: is a function of v over c. O is receding; it's running away from the light ray, and so we know that the Doppler shift is going to reduce the frequency. So we pull out the Doppler shift for that situation where the observer is receding away from the light ray, and so it's of the form of 1 minus v over c, a reduction, divided by 1 plus v over c, where v is the velocity at which O is moving at the time of receiving the light ray. Well, I can simplify this thing as a square root. It's a complicated function of v over c, but I'm only working to first order in v over c. Okay, and so for example, 1 over 1 plus v over c is approximately 1 minus v over c upstairs, and multiplying things out and keeping everything just the first order. It's approximately 1 minus 2v over c, square root of that. Taking the square root, again, that eliminates the factor of 2 when I just do the algebra to get it to first order in v over c. Okay, so it's just 1 minus v over c, and I know what that is over here. The velocity is just gh over c, and so the correction is a minus gh over c squared. Why minus? Well, you see, that's because O is moving up away from the light ray. So the Doppler shift is a shift downward in frequency, and there you have it coming out of the algebra. Okay, and so I see there's a change in the frequency, and so I can write that as a fractional change of the frequency, as done here. Nu at the observer minus nu at the emitter, divided by nu at the emitter. Right, that is delta nu over nu. And what is that? Well, that just isolates the second term in this formula here, and it's minus hg over c squared. Okay, so that's how the frequencies transform. But I can also get a more fundamental view of the phenomena. Frequencies goes 1 over time, okay, 1 over the period of the oscillator, and so replacing nu by 1 over nu. Replacing nu by 1 over t, I mean. Okay, I don't even have to think about the proportionality of them because this is homogeneous here. So I see that if delta nu over nu is minus hg over c squared, then delta t over t will be plus hg over c squared. Okay, and that's the final result. From that, I can then tell you how much the redshift occurs as I shoot light from one point of position R to another point of position R, perhaps radially away from the planet. Okay, and I also see here I did it for the case of a potential that I can write as g times h. But what's upstairs here is the potential difference in general divided by c squared. But for small differences and such, okay, where the gravitational acceleration is uniform, I can write that just as the potential difference as h times g, and that's what I do here. Okay, and so it's stated then. The observer at h observes a redshifted ray. Frequency goes like the reciprocal of time, so the observer O concludes that E's clock runs slower. Okay. Effectively, O is observing the ticks on the clock of E. Okay. The frequency is redshifted, and so the ticks come in at a slower rate, and there you have it. Okay. Now there are other approaches to this problem, and they're interesting, and they'll come up in our other applications. So let's take a look at them. Here's one. We can think about energy conservation. Okay. So so here I imagine a pulley system. Okay. A fixed pulley system. It's in a gravitational field, and I have and I have an observer on one side and an emitter on the other side. They're at a different distance, different height of h. And the fellow at the lower level shoots a light ray up to the one at the higher level, which absorbs it. Okay. Well, just thinking in terms of special relativity, what would happen? Well, the light ray, of course, carries energy, and energy has a mass equivalent. So he's effectively transferring mass from here up to here. Okay, so if things were in equilibrium in the original picture, and then he shoots the mass from here to here, then we're out of equilibrium, okay? And this side is heavier, and it gets pulled down. Okay, and so we end up with a situation like this. Okay, but this is the original situation that we had, and so this fellow down here can shoot a light ray up and continue the process. Okay, well, work is being done in each one of these steps. The pulley is pulling this guy up and this guy down. That could be the basis of an engine, and so it looks like we have a violation of energy conservation and an infinite source of energy, and we have a perpetual motion machine. Okay, well, now we got to think about this from the perspective of the redshift. The only error we made in this analysis, okay, is to account for the fact, okay, that the frequency of the emitted light is not the frequency of the absorbed light. Okay, we just learned, okay, that the frequency is diminished in a specific way. Okay, so light carries a mass equivalent of energy over c squared. So when the heavier mass descends, h, it does a work which is just mass through the potential difference, and it's written down here. Okay, so E times delta V, the change in the potential, over c squared. That's the amount of work that's done by this device as you go through one cycle. Now let's correct it for the redshift. Okay, when the light arrives at the second mass, okay, its frequency is diminished, and we know how much that is. The fractional change in the frequency is minus the change of the potential over c squared. Okay, but for a light ray, as we discovered in special relativity, the frequency transforms like the energy. And so if you have a fractional change in the frequency, you have the same fractional change in energy, and we see that the fractional change in the energy is minus delta V over c squared. So that means when the light goes from here to here, its energy is diminished by delta V over c squared times E. Oh, but that's exactly the energy we expected to get out of our perpetual motion machine. Okay, so in fact, we get nothing out of the perpetual motion machine because of the gravitational redshift. Light arrives with a diminished energy, which is this, and nothing in fact has been gained. What we learned from this, basically, what we're going to take from this is the fact that we can think about the redshift as a consequence of energy conservation. I motivated the discussion by imagining a pulley system and a perpetual motion machine, and what we learned from this, in fact, is that the perpetual motion machine fails because energy is conserved, and that's implemented by the redshift. Okay, the amount of energy you thought you were going to gain by the perpetual motion machine is just the amount that's lost due to the redshift, and so nothing is gained. Energy is actually conserved, and the machine does not do the work that we expected of it. Okay, so another perspective on the redshift. We'll see this play out when we do more on general relativity. Okay. Now, along the lines here, we see that we went from a problem in frequency to a problem in time. Okay, and I can also continue to assimilate this result into the formalism of general relativity, and that's done in the lecture series and in the textbook. We learn that the way to assimilate this into the metric, okay, is that this causes a slight deviation from the Minkowski metric. Okay, the zeroth component of the Minkowski metric is no longer 1, okay? It's 1 plus twice the potential over c squared. Okay, just the effect that we found here in the redshift. So as we move forward in these lectures, we'll come back to it. We'll assimilate the redshift in that language and move forward. Now some of the discussion that makes that point quantitative is in the lecture series. So take a look at that. We'll have a number of times where we'll be coming back to linear weak gravity, and we'll rediscover this effect at several different stages. But let's just make a note of it here that this implies, okay, that the space-time metric in the vicinity of the planet is no longer Minkowski-like. It has a small correction, which is that G naught is no longer 1. It's 1 plus a correction of order 1 upon c squared, which is proportional to twice the gravitational potential at that particular point. Okay. The spatial dependence of the metric then encompasses the fact that the redshift, of course, varies as you move around the planet, depending upon how strong the gravitational potential is. So take a look at the notes. We'll be covering the same issues in recitation section, and I'll leave the formalism to the notes and the recitation system. I just want to emphasize here the concepts involved. Okay. Well, another concept here is the twins again. Okay, we can get another perspective on the twin paradox. Okay, now that we're armed with a little knowledge of general relativity in the form of the redshift. So let's recall the twin paradox of special relativity. We had two space travelers. There was the conservative person Mary, who stayed at home, and her time path is shown on this Minkowski diagram, going from 0 to 10. She ages 10 years, just sitting there. Now her irascible younger sister Maria, okay, well, twin actually, I should say, younger in spirit perhaps. Maria takes a rocket ship at a good velocity away from Mary. Okay, after Mary has aged 5 years, okay, Maria has second thoughts and jumps on an inbound rocket ship to come back. Okay, over that course of that process, Mary ages 10 years, and Maria notes that lo and behold, she ages only 6 years. The result being the twin paradox, which we resolved in our discussion of special relativity. And what was the resolution of that? Okay, well, the resolution was that the lines of constant time are frame dependent. It's the relativity of simultaneity. So from Mary's perspective, okay, she's just sitting here at x equals 0, doing nothing, and the lines of constant time for her are just these lines parallel to the x-axis. Okay, and so she views Mary's clock, and by time dilation, okay, she ages 5 years, okay, as and over a period where Maria ages by 3 years. Okay, and that's just time dilation for the particular b over c that's chosen in the problem. Okay, and so Maria keeps an eye on. So Mary keeps an eye on Maria's clock, and does decide that when she is aged 10 years, that Maria has only aged 6 when she comes back, and so Maria ends up as being her younger sister, which bothers Maria considerably. Okay, what we have to do to resolve a paradox, of course, is to look at from both perspectives and get the same answer from both perspectives. From Mary's perspective, we got a perplexing answer, perhaps. Okay, but it was a straightforward analysis. From Maria's perspective, it's much more involved. Well, we do the same thing for Maria as we did for Mary. We look in Maria's frame for the lines of constant time. Well, the lines of constant time are shown as the dashed dotted lines in the picture. They're the lines that follow from the Lorentz transformation, over which Maria says those are times of a fixed time in her frame, and they are bent in the downward way. Okay, and so review that in your special relativity, and you'll find, of course, when Maria hits 1 year on her clock, okay, it's 0.6 on Mary's clock. 2 corresponds to 1.2, and 3 corresponds to 1.8. Okay, so from Maria's perspective, okay, she gets to the midpoint, okay, of the travel, and she looks back at Mary, and she says, "Oh, Mary, you're younger than I am by the same factor that you think I am younger than you. 3 is to 5 as 1.8 is to 3. Okay, so we see time dilation working from both perspectives. Okay, but now things happen. Okay, now Maria jumps from the outbound rocket to the inbound rocket. Okay, so the velocity is reversed, and so the lines of constant time in Maria's frame are now new. They correspond to a rocket which is going at minus v, not a rocket that's going at plus v. And the lines of constant time are then shown here, dash dotted again. The relation of the path of the rocket going out to the lines of constant time here is the same as the path of the rocket here to the lines of constant time here, because it's just v goes to minus v. Okay, so take a look at that in the discussion of the twin paradox for special relativity, and verify that. Okay, and again, Maria sees time dilation of this variety after she's made the jump. Okay, but the critical point in the picture is, of course, the amazing thing that happens at the jump. Okay, the lines of constant time swivel from here to here, and a gap opens up on Maria's time axis, on Mary's time axis, and Maria says, although she ages just the bat of an eyelash in the turnaround, Mary, from her perspective, has aged 6.4 years. Okay, so something discontinuous has happened, and it shows up in a discontinuity in the aging process of Mary from the perspective of Maria. Okay, it's from one's perspective to the other. Mary is just sitting there on her clock. Everything is fine. It's just clanking along on a regular basis. But from Maria's perspective, a great change has happened in the turnaround, in that period where there was acceleration, where she goes from a velocity of plus v to minus v. Okay, and in that period, Mary has aged 6.4 years. That brings in the asymmetry, and that explains the twin paradox. Okay, this change of 6.4 then giving rise to the fact that from Maria's perspective, she sees Mary age from 0 to 1.8. Okay, and then another 6.4 years to 8.2, and then aging from 8.2 to 10, as shown on the picture. So the picture has all of the twin paradox right in it. Okay, the Minkowski diagram has the issue in there, and you see what it is. And the great surprise, of course, being the fact that from Maria's perspective, Mary ages a great deal, and Maria has the acceleration. Okay, so there it's stated. Okay, but now let's take a look at that acceleration. From Maria's perspective, Mary goes out and back, and by the equivalence principle, Maria's acceleration can be replaced by a gravitational field. Okay, she jumps from one rocket to the other, or one could say she's in one rocket that has an acceleration from minus v to from plus v to minus v in a very short period of time, and that's the way I want to look at it, because I want to look at uh, her aging and Mary's aging process from the perspective of the rocket, and using the equivalence principle. So here's the event shown in that way. Okay, so here we have it as an acceleration. Okay, after a time period, capital T, where the distance between Mary and Maria in Mary's frame is vt, Maria undergoes an acceleration, change in velocity over time. Time is just some click of a clock over which her velocity changes by 2v. Okay, the important point here is that it is the acceleration, of course. Okay, but t has to be if I have a big v, t will be a small number, so that I capture the picture that we had in the previous case where the acceleration was almost instantaneous. So I can replace the acceleration problem by a problem in gravity. Okay, where Maria is now experiencing this acceleration, and so she's in a uniform gravitational field with a g of A, okay, gravitational field strength A, and that's applying uniformly over her environment. Okay, so now she just thinks redshift. At the turnaround, Mary says the distance to Maria is vt. Okay, that's fine. The gravitational potential difference, therefore, in this picture, is just the gravitational field times the distance. Okay, with a uniform gravitational field of size A, and so A times distance is the change in the potential. Okay, so according to the redshift problem, we know that Mary's clock gains time, which is given by the change in the potential over c squared times t, the time over which it's applying. Okay. Well, what is that time? Well, I see that time is related to the acceleration and the velocity, so I get rid of t, okay, in favor of the velocity. Here, the combination you see is a times t, and a times t is 2v. So I put that into the formula, and so that's a good formula. Okay, I introduced the little time t just to tell me how long the acceleration period was, but what comes in to the formulas is the acceleration times that time difference, and that's just twice the change in the velocity. So this then is the time difference that Maria would say that Mary has experienced during the period where the acceleration applies. See, Maria is at this position in the gravitational field, and Mary is at the higher gravitational potential, and we've calculated the difference over here. Now let's put in the numbers from from our discussion of special relativity. I remember that t, the time on Mary's clock at the turnaround, is 5, halfway through the journey from Mary's perspective. V over c was 0.8. That was the case we chose because the numbers worked out slickly there. And so Mary's time gain is just, twice t, 2 times 5 times v over c squared, 0.8 squared, and that's 6.4. Okay, so we got the same answer that we got before, and all is well. We can understand, okay, that Mary ages more than Maria in the split second when Maria is feeling the acceleration, because Mary, in the gravitational analog, is at a position of higher potential. Okay, and there's the details. So and so that gets us the 6.4 asymmetry, and we put all the pieces together, and we learn that over the course of the whole trip, Mary ages 10 years and Maria ages 6 years. Okay, now the only complaint you might make about this discussion is that these numbers are pretty big, and I only derived this the redshift for weak fields, okay. So we have a little work to do, okay. We'll have to come back to the redshift and discuss it in general and see that in fact this derivation is correct. Okay, okay. That in the uniform field, this is an exact discussion. Okay, and we'll do that later. We'll take a look. We will get the redshift exactly in strong fields later, and see that we really can justify the discussion, and that's fine. And in the textbook, you'll also go back there and discuss it from the perspective of the relativity of simultaneity in special relativity, and also verify its correctness. And so that's fine. And that's really what you want to do. Yeah. So I think that's a nice demonstration. We've dissected the twins in many different ways. Oh, and I think I'm going to do it one more way later. That's right. I'm going to do it one more way later because I'll want to consider a spaceship which has a constant acceleration, okay, and do it using special relativity formulas, and just discussing accelerating clocks. How to accelerating clocks. What gets a problem in special relativity? It'll lead us to a topic called the Rindler space-time, which is a space-time of constant proper acceleration. So we'll even take another look at this and have very different formulas and get the same effect again. Okay, so that'll be quite a lot. That'll be quite a lot of fun. Okay, so our next topic will be to contrast electromagnetism and gravity. We know a lot about electromagnetism. We're beginning to learn about gravity. Let's take a look at what the similarities are and the differences are. Okay, just to get a perspective on that, and we'll stop that next time we meet. Thank you.